Hi, I'm Norman Wildberger, and today we're going to introduce green geometry, which is a variant to red relativistic geometry that we've been talking about in the last few videos. Alright, so what is green geometry? Well, let's start by reviewing the blue and the red ones. Here are 2 points, A1 and A2, with coordinates x1, y1 and x2, y2. The blue quadrants between them, the standard Euclidean quadrants, is the difference between the x-coordinates squared plus the difference in the y-coordinates squared. That's what we've been studying for most of the videos in this series. The red quadrants between those 2 points is the difference between the x-coordinates squared minus the difference between the y-coordinates squared. And today we introduce the green quadrants between the 2 points, which is 2 times the difference between the x-coordinates times the difference in the y-coordinates. The green quadrants between 2 points. So our first theorem connects the 3 quadrants. So if we have 2 fixed points, we can measure the quadrants in these 3 different ways. And the theorem says that the blue quadrants squared is equal to the red quadrants squared plus the green quadrants squared. So it's already telling us that these 3 different notions of quadrants are intimately related. And the proof is an immediate application of this very fundamental identity, which is, next to Fibonacci's identity, the second most important identity in mathematics, probably. It goes back to the Pythagoreans. And it says that r squared plus s squared, all squared, equals r squared minus s squared, all squared, plus 2rs, all squared, for any values of r and s. In particular, if r equals x2 minus x1 and s equals y2 minus y1, then this is the blue quadrants squared, this is the red quadrants squared, and this is the green quadrants squared. So this identity proves this theorem. Each of the 3 geometries is characterized by a particular notion of perpendicularity. The blue familiar perpendicularity is telling us that if we start with the vector v, AB, that's the vector v, AB, then perpendicular to it is the vector minus BA in that direction there. So this is blue perpendicularity, that's the usual familiar one. The red notion of perpendicularity is that this vector v equals AB is perpendicular to this vector BA. In other words, that's the reflection of the original vector in the line of slope 1. Or, if you like, in the line of slope minus 1 up to a scalar. Now we have a new notion of perpendicularity, the green notion, which is that the vector AB is green perpendicular to the vector minus AB. This vector here is green perpendicular to this one here. Now the connection with the quadrants is that in each of these cases, these pictures are defining us a square. And quadrants, back to the ancient Greeks, is the area of a square. So when we measure the blue quadrants between these 2 points, what we're really doing is measuring the area of this square. And when we measure the red quadrants between those 2 points, what we're really doing is we're measuring the area of this square. Well, it doesn't look like a square to us, but it's a square in the red setting. And when we measure the quadrants in the green framework between these 2 points, what we're really doing is measuring the area of this green square right here. So how do we know that, or how can we check that? Well, we have to remind ourselves about the formula for the area, or more particularly the signed area. Here is a vector xy, and here is a vector uv, and those 2 vectors form a parallelogram. And the area, or the signed area of that parallelogram, can be given by this formula here. And for those of you who have seen determinants and matrices, you can write it as determinant of xy uv, which is x times v minus y times u. So this expression here describes the area of such a parallelogram. And it's an expression that's independent of a notion of perpendicularity. It's a purely affine notion. So if you take the these two vectors here and compute the area formed by them, you get a squared plus b squared. That's the usual blue quadrants. If you take these two vectors, you get a squared minus b squared. That's the red quadrants. And if you take these two vectors, you get ab minus ab. So that's 2ab. That's the green quadrants. So this formula really does recover the three notions of quadrants from these three notions of perpendicularity. Now there's a slightly more sophisticated way of approaching what I did on the previous slide, which uses the idea of an inner product, which is part of linear algebra. But we're not going to use any linear algebra in any serious way here, so let's just think of the inner product in a very naive, direct way. If we have two arbitrary vectors, a1, b1 and a2, b2, then we can express the perpendicularity between these two vectors in terms of this expression here. If we take a1, a2 plus b1, b2, then if that's 0, then the two vectors are perpendicular. So, for example, if you had ab and minus ba, and then you compute this expression, you would get 0. So this number, which is associated to these vectors, is called the inner product between these two vectors. Sometimes also called a dot product. Okay. So it's a number that's associated to two vectors that tells you when those two vectors are perpendicular in the blue sense. Well, in the same way, there's a red inner product that tells you when two vectors are perpendicular in the red sense. And it's just a variant on this one. It's a1, a2 minus b1, b2. So you can check that the previous example of red perpendicularity is captured by this expression. And in a similar way, there's an inner product that represents the green notion of perpendicularity. Two such vectors are green perpendicular precisely when a1, b2 plus a2, b1 equals 0. So we have these three inner products, the blue one, the red one, and the green one. And we'll see that these three inner products have beautiful connections with each other. There's a fourth expression that's important to mention too, which is expressing when the two vectors are parallel. So two vectors are parallel when they're multiples of each other. In other words, when this ratio is equal to this ratio, or this proportion is equal to this proportion. And that's the expression a1, b2 minus a2, b1 equals 0. All right, so once we have this notion of green inner product, we can use it to define the notion of the spread between the two vectors. Because we had this basic formula for a spread between two vectors, which can be expressed in terms of a dot product like this. 1 minus the dot product of v1 with v2 all squared divided by the dot product of v1 times the dot product of v2. And that then turns out to be independent of scaling of v1. If you multiply v1 by 3, then this quantity doesn't change. And there's a 1 minus here to ensure that when these two vectors are the same, we get 0. Okay, so now it's a good exercise for you, please do it, that if you use this as the expression for the dot product, so that's v1 and that's v2, that's v1 dot v2. So if you take that expression and plug it in there, and then also similarity here and here, and then you simplify this expression, you will get this. So this is the specific formula for the spread between the two vectors a1, b1 and a2, b2. It's a number. There's a minus sign here, and in the denominator we have the product of all four quantities. So now we have the notion of green quadrants, notion of green spread. We can do trigonometry, and next time we will. We'll also talk about green circles and how they're just variants on the red circles. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.